So, welcome to this class on hardware security. So, we shall be continuing our discussion on difference of mean as we have started in the last class. So, in particular today we shall be taking a more deeper look into how DOM works and can be applied on standard block ciphers like AES. I shall be explaining or formalizing the selection function in more details, and then we shall be seeing some snapshots or case studies on what are the results of DOM being applied on actual power traces on AES, DES and 3DS, and then I will summarize our discussions on difference of mean. Let us see how the DPA can be adapted for AES, right, which is essentially a standard cipher, and we have already seen how the AES design works. So, imagine that you have a AES hardware, and what we try to do is we basically observe now the power consumption for say 1000 AES encryptions, and imagine that there are something like 10 to the power of 5 data points per curve. So, this is arranged in the form of a tuple. So, like along with the cipher text, I also observe the power trace, which is called as the curve. Okay. So, this we kind of indicate by the tuple cipher text I comma curve I to indicate that along with the cipher text you are also observing the corresponding power trace. Okay. So, now we assume a key for an S box of last round, okay, of the last round. So, note that in the last round key, right, you have got 16 S boxes and the total key has got a dimension of 120 bits. Okay. And as I have said previously also, this attack is essentially a divide and conquer attack, which means you do not guess the entire key together, because then it will be like a brute force attack, but rather you try to do the attack part by part. So, basically you guess parts of the key, like in this case it is a byte of the key which you guess. So, I guess say one of the key bytes which I want to kind of determine, and I guess that. Okay. So, in that case I guess one byte of the key, that means 8 bits of the key. So, now when you essentially guess that, you essentially can calculate the last round first bit input of each cipher text using the assumed key. So, note that you are observing the last round S box, and as we will see later on is that you have the selection function which will basically determine the last round. Say you have in the last round there are 16 S boxes, okay, and you basically target any one of these S boxes, okay, depending upon your diffusion function, and then you basically once you target that S box, you know that there are 8 bits which are going as an input to the S box. Okay. So, your target bit can be any one of them. It can be the 0th bit, can the first bit, second bit, or the 7th bit, which is like all the 8 bits actually. And then so what you do is that you basically like you have got the cipher text, you guess the last round key, you go to the input of that S box and you find out say the LSB of that bit. Okay. And why you do that? You basically use it to partition your traces, okay, as we have seen in the previous example also. So, that bit can take either a 0 value or can take a 1 value. So, if it is 0, then you put the power trace into the 0 bin. If it is 1, you put the power trace into the 1 bin, okay, as simple as that. So, therefore, you divide the measurements into 2 groups depending upon the output 0 and the 1 of your selection function, and you calculate the average curve of each group. So, each group will have the 0 bin will have some power traces which are going into that, the 1 bin will have some power traces which are going into that. You take the average of each group, okay, and then the idea is that you calculate the difference of the two curves with the hypothesis that if your guess was correct, then your differential curve, that means when you are taking the difference of the averages, will have some place where there is a non-zero spike. Okay. Note that if you are observing the differential curve, you are plotting the differential curve with respect to time. Okay. So, there are different instances of time when the actual computation does not take place. Okay. So, in that case, even if your guess is correct, that difference, right, in that particular time instant when you are not doing the actual operation, we will still have a 0 value, we will still have a like close to 0 value or negligible value. But when you are actually doing the operation on which you are essentially trying to correlate by getting the last bit of the S or like getting one of the bits of the input of the S box, then you will find that there is a non-zero difference. Okay. For example, like if you are doing the splitting targeting one of the S boxes, right, and observe that when you are plotting the power trace is plotted with respect to time. Okay. But there is only one time instance when that S box is really coming into play. At other time instances, right, even if you are taking a difference of mean with the correct key guess, you will still get a 0 difference of mean. Okay. But when you are actually doing the difference of mean, right, and you are doing it exactly at the time when that S box is coming into play, then you will get a non-zero difference of mean. But for the wrong guesses, you will always get a close to zero, like difference of mean, and therefore, right, for the correct guess, you will find that there in the difference of mean will have like small values and then a peak, okay, and that essentially will distinguish the correct key from the wrong key. So we will see some examples, and we repeat this operation for other key bytes, okay, and therefore using divide and conquer, you basically retrieve the entire secret. So now let us look into DOM in slightly more mathematical way. So therefore we have a selection function, as I have tried to kind of motivate. Let us kind of denote that selection function by the function D, okay. The function D operates on ciphertext. There is a target bit denoted as B, so it could be the 0th bit, first bit, or any other bit position, and then there is a part of the key which I denote as KS, which is your guessed key, okay. So this is used or defined, this is used to basically get the value of the target bit. The idea is that, so as I say that this is a bth input bit depending upon the C ciphertext and also the KS, which is the guessed 8 bits of the key. If your case is incorrect in evaluating D, then this will still give you the correct bit in some cases, because remember that it's in that case it becomes like a pseudo-random function, and therefore, right, with the actual bit, okay, which is there in in your like which is essentially getting computed by your hardware, because your hardware knows the correct secret, because the correct secret is suppose embedded in your hardware, okay. So therefore, right, even if you are guessing wrong, sometimes you will be able to correctly predict it and sometimes it will be wrong. So therefore, you can imagine that half of the cases or around half of the cases it will be correct and around half of the cases it will be wrong, okay. That is why this bit will then like this output of the selection function will therefore operate like a pseudo-random function, okay. But if your guess is correct, then all the time it will correctly match with your correct like it will correctly match and correctly predict that corresponding bit, okay. So therefore, right, this is a very important point to be noted, and essentially is the reason why your attack works. So what the attacker does now is that attacker obtains M encryption operations, okay, and captures, as I said, M could be like 1000 encryption operations, and captures the power traces in the form of a table, okay. So you can imagine that the table is something like denoted as T1 to M to 1 to K. So the idea is that you have got some rows and some columns, okay, and the rows essentially are like denoting the various power traces or various executions that have taken place, whereas the columns are different time instances of your power traces, okay. So attacker records the M ciphertext also, because the ciphertext will be used. So you can basically do the attack in a setting where no knowledge of the plain text is required. So it is kind of working as a ciphertext only attack. So now, so this is an example of how like how your power board can look like. So you can see that this essentially is nothing but your ciphertext, okay, the various ciphertext that has been observed. For every ciphertext, you see that that means, so every ciphertext, suppose this ciphertext corresponds to an encryption operation of AES, and what we have observed, right, is the corresponding power trace of AES. So how do you kind of plot the power, or how do you note the power trace of AES in this table? You basically sample it at different time instances, okay, and then you find out the corresponding real value, and that real value is say stored in this table, okay. So imagine this T111 stands for the fact that in the first row at the first time instance when you are sampling it, what is the corresponding power value, okay, and likewise you essentially stored this in this entire column, entire row, okay. And likewise you have got different executions, like you go to the next ciphertext, again you take a different power trace, and that is also being kind of plotted, kind of noted here. So you essentially have kind of like represented the power trace in a tabular fashion, okay. So with this, so this essentially is stored in your computer. I mean, is captured by the oscilloscope and then again stored back into the PC, where you essentially keep this data, okay. So now we are all, so now let us see how we can do the subsequent steps of the attack. So what we do basically here is, let us look into AES as a specific example that we are discussing of, and imagine that this is the last round of your AES algorithm, okay. So, here you have got, so this imagine is the input of, imagine that is the input of your AES. So, let us basically take this slide rather, this is probably more clear. So, you take this, so consider AES 128, okay. So, so you consider AES 128 and imagine that, so this is the last round of AES. So, the input, the operation is sub byte, which is the S box, followed by the shift rows, okay. So, imagine that I want to know, so what you do in, so let us first of all see the, just recapitulate the algorithm. You have got like this state matrix, you perform the sub byte and the shift rows. Sub byte is just byte by byte substitution and then you follow it by a shift rows. Shift rows, first row there is no shift, in the second row there is a circular left shift by 1 position, third row there is a circular left shift by 2 positions and in the final row there is a circular left shift by 3 positions, okay. And then you do an add round key. So, basically you XOR this secret key, which is again 128-bit key, and you get the cipher, okay. So, now imagine that as an attacker you are interested to know in this part, this byte of the key. Likewise, I will recover each of the bytes, okay. So, that is why it is a divide and conquer attack. So, what I do is therefore, I take the corresponding cipher text, say C10 here, and I XOR them and I come here, okay. Then I know that for this guess, say the guess is K star, this value is say C10 XORed with K star, and then I go inwards, that is I take the inverse operation and I come to this position. You see that there is a shift row operation, because of which this position corresponds to this position, okay. And therefore, what I do is therefore, I take S inverse of C10 XORed with K star and I can target any of the bit positions here. Suppose in my selection function here B is equal to 0, that means I am targeting the LSB of this state. So, therefore, I take this S inverse C10 XORed with K star and I found out the LSB of this particular state, okay. So, the idea is that if this particular LSB is 0, then the corresponding power trace that I am capturing, right, because I am capturing a corresponding power trace also. So, this power trace, if this LSB, right, is essentially 0, that means if this bit turns out to be 0, then I will put this into the 0 bin. So, I will put this into the 0 bin. On the other hand, if this turns out to be 1, I will take this power trace and put it into the 1 bin, okay. That is a simple idea. So, now what I do is I again take the 0 bins and the 1 bins, I take the average of each of these bins, I take the difference of these bins. If my key guess was correct, then I would expect a non-zero difference of mean. Why? Now, because that means that if my guess was correct, then the LSB that I had calculated will actually match with the correct value for all the ciphertexts, okay. However, if it was wrong, it will match roughly half the times, assuming sufficiently large number of cipher samples have been collected, okay. So, therefore, right, in that case, when your guess is wrong, then the splitting of the power traces is done kind of in a random fashion, and therefore, you would expect that again the sum or the average in both the bins will be roughly same, and therefore, the difference of mean will be close to 0, okay. So, that is essentially the basic crux of the idea or idea of why the DOM attack works, okay. And you can actually mathematically write that in this fashion, okay, the same thing. So, essentially the simple idea, but written in a more formal way. So, you can see the attacker now obtains a K sample differential trace delta D. So, this is your differential trace by varying the difference between the average of the traces for which this selection function was 1 and the average for which this selection function was 0, okay. So, for example, this part of the computation, like if you observe this part, essentially you see that it turns out to be that when the selection function was 1, right, if the selection function computes to 1, then that means you are basically taking those power traces for which the selection function corresponds to 1. So, therefore, this sigma, okay, or this average is the average for the 1 bin, okay. On the other hand, this essentially stands for the 0 bin, because if this value computes to 0, then only this power trace is kind of taken in your sigma. So, therefore, this average stands for the 0 bin, and therefore, what you are computing here is nothing but the difference of the bins, okay. And the rest of the thing is essentially is exactly as we have seen in the previous discussions. So the idea or the principle is that if Ks is wrongly guessed, then D behaves like a random guess. Thus, for a large number of sample points, this delta D 1 to K will tend to 0. Okay. But if it is correct, then the differential will be non-zero and will show spikes when D is correlated with the value being processed. That is, when your actual S box which you are targeting, for example, is being processed, at that point you will see in the differential curve, if your guess was correct, you will see non-zero difference of means. Okay. So it is very interesting in the sense that you can do such an attack, and the attack, more important is that the attack works in real life. Okay. So here are some examples on actual power traces being accumulated on AES, for example. And as you can see that we know that the correct key byte that we are targeting, say, like we are targeting, say, the 11th S box, for example. And as I say that you can target any of the bits actually. So in this case we have targeted, say, the 8th bit, for example. So something with 15,000 power traces, okay, you can see that the correct key is showing up differential spikes. Okay. And therefore these distinguishable spikes are not, since they are not prevalent in the other key bytes, then it implies that this is the correct key byte. Okay. So likewise you can do the attack on any example, you can do the attack on DES also, you can do the attack on your trace counts will probably vary depending upon your implementation, depending upon your target algorithm, but what stays like as a central truth is that all these implementations, if they do not take care of this kind of attacks, they are vulnerable to such kind of techniques. Okay. So you can also try to apply it on triple DES, and even there like you can find these distinguishable spikes which will distinguish the correct key byte from the wrong key bytes. Okay. So here is a summary of what we have already studied, okay, in a more I would say systematic fashion. So and in a more generic fashion, you can, if you understand this, then you can virtually implement this on any block cipher or any algorithm for that matter. So here you see that we have observed what we note here is like the various plain text or the cipher text. So you can do the attack in any mode actually. So imagine that they are all cipher text. So you have got, say, capital D cipher texts that we have observed. So you have got capital D ciphers, and there are K values for a key byte. Okay. So in the case of AES, there are 256 values for the key byte. So all these are your key hypotheses. Okay. So there are K hypotheses which are possible. So the K can take, the key can take capital K values. Okay. So now what you do is basically you do an XOR, okay, and then you do an S box. So you can do an inverse S box when you are operating from the cipher. You can also do the attack from the plain text. If you are doing the attack from the plain text, right, so this could be either D ciphers or it could be D plain text also. Okay. The plain text means the message that you are encrypting. So suppose if you are, so we have already seen when you are doing the attack with respect when you are operating from the cipher. So you can also do the attack from the plain text. Okay. So suppose these are all D plain text, I kind of XOR all my key hypothesis, I target any one of the S box. Okay. So for example in AES, so imagine that this is your state matrix, okay, and the plain text comes in between, right, this is your plain text and it kind of gets XORed with your secret key, and you operate your S boxes. So there are 16 S boxes, I can target any one of the S box. Suppose I target this S box. Okay. So if you target this S box, then that means that suppose I guess the P00, which is like one byte of the plain text, I XOR it with my secret key, say K00, and then I apply my S box. Okay. So this S box will produce again an 8-bit of output. Okay. And these are essentially what are called as the hypothetical S box target bit values. Okay. So it is interesting that we have use this word hypothetical, which will probably make more sense when we discuss about the next attack method, which is called as correlation power attacks. But this is a term which we can use in a more generic setting. Okay. So that means, so therefore the idea is that you have got a hypothetical. So the reason why I am saying hypothetical, because it depends upon the key hypothesis. Okay. Whether your hypothesis was correct or not, depending upon that, your bit value will be correctly estimated. Okay. So here you observe that for all the D values, we have basically guessed the key, and how many guesses do I have? I have got K guesses. Okay. So, therefore, right, I have got k guesses here which stands for the columns here, and the rows stands for all the d observations that I do. Okay. So, imagine that I make a guess here, and then I do it for all the corresponding d plain text. I evaluate the output of the S box, okay, and I target any one of the bits. So, I target maybe the like now let us target the MSB for example. Okay. So, then I get, so what I do is that for all these values, right, I will, so therefore this value can be either a 0 or a 1, okay, and depending upon that I classify the power traces into the bins based on these intermediate values. So, that means, right, the corresponding power trace P11 and P21 and so on till Pn1 kind of indicates those power traces which has gone into the 0 bin, okay. And likewise these power traces indicate, right, those power values which has got into the 1 bin, okay. And then I take the mean. So, I take this mean mu, I take this mean mu here, and I take the difference, okay. So, this essentially is also called, this difference of mean is also called as DPA bias, okay. So, I calculate the DPA bias for all my individual key hypotheses. So, I have got DPA bias 1 to DPA bias k, okay, and my correct key computation is calculated by this argmax function. So, what it does is that it takes all the DPA biases, compares them, and you can see that there are k such candidates, finds out the maximum and the corresponding key value is returned as my candidate key. So, you can easily observe that since this is a statistical attack with less power traces, you will have lot of candidate keys, okay. But as you are kind of progressing and observing with larger number of observations, the correct key hypothesis will stand, whereas the other ones will fall off, okay, and therefore, the separation will be more will be better, okay. So, that essentially is basically more or less the summary of like what essentially we had to discuss about difference of means. And so let me just so this is the reference that we have used. So, this is the standard textbook. So, just to summarize, what we have discussed is the DPA works because of the dependence of power consumption on state bits. DPA works because of the fundamental way of computation, as we have seen that it works independent of the algorithm, but it works more because of the way in which we do computations, okay, and therefore, right, it is more fundamental, and therefore, right, if you really want to stop DPA working, you need to understand how the countermeasure should be built. So, we discussed in particular about the difference of mean, which is one of the classical forms of doing a side channel attack, and we also applied DOM to a toy cipher, which is essentially which was implemented using the exponentiation routine, and we also applied DOM for AES. So, in particular, we apply the DOM for the advanced encryption standard and how it can work both from the ciphertext as well as from the plain text, okay. So, we also kind of try to understand how the DOM works on a very generic setting, okay, and therefore, right, with this background we should be able to write a simple program to automate the calculation of the difference of mean, okay. So, let me stop here, and thank you for your attention.